Thank you for inviting me to join you. I really appreciate the Hertz Foundation's willingness to let me pollute your afternoon or morning or evening, depending on where you are. Uh, Second, I thought I would show you what I'm wearing on my lapel here. I don't know if it's too obvious. It's an alligator. And some of you may remember the old joke about the guy that's sent off to drain the swamp. And they call him up 6 months later and they say, "How you doing draining the swamp?" And he says, "Let me tell you, when you're up to your ass in alligators, sometimes you forget your job is to drain the swamp." And I've been up to mine for 50 years in internet alligators. And so I thought I should get to know them. I have a collection of about 150 alligators at home. They're not live alligators, they're little gold ones and glass ones and ivory ones and wood ones and so on. And I'm very fortunate. My wife is an interior designer, and normally you wouldn't expect her to tolerate having alligators all over the place. But she's been fairly tolerant as long as most of them stay down in the basement, so they're not overly visible to our guests. Well, I'm going to show some slides to you, but I want to emphasize a point that was just made earlier that Sandeep made, which is that connectivity in the internet is literally everything. In the absence of connectivity, it just doesn't work. And it has to be a free flow. So the architecture was designed to be insensitive to geopolitical boundaries. It was a very deliberate decision that we made, Bob Kahn and I, when we did the original design work starting in 1973. So the reason for that is that it was being designed to support the American defense interests, and we knew that the network would have to be functional everywhere in the world, no matter where we went, and it also needed to support our allies. And interestingly enough, this is 1974. We were asking ourselves, okay, so who are our allies? And there was a list in 1974. And then we asked the question, well, who were our allies 25 years ago? And it turned out to be a different list. And then we said, well, who will our allies be 25 years from now? And the answer is we don't know. And in order for this to serve its function, its specifics needed to be available to all of the allies so their command and control systems could interwork with ours. And so we decided to release the design publicly with no patenting, no limitations on who could use the design, could implement the protocols. And a lot of people have said, well, how the hell did you get away with that? And the answer is, well, we just did it and nobody noticed. So, it didn't matter. That might not be the case today if we had tried to do the same thing. But it turned out to be very important because that facilitated the adoption of the system. So, with that, and the other observation to make about this connectivity being so important, with the advent of the World Wide Web, the ability for any computer on the network to touch, reach, interact with any other computer, any other willing computer, is essential. Otherwise, the web doesn't work. And it's easy for you to understand that if you think a little bit about what a browser does. A browser reaches out across the network and pulls in a file from some website and proceeds to interpret the file. And what's in that file might be not only text and formatted text and some imagery and maybe some other, streaming audio or video, but it may also have all kinds of references, URLs, uniform resource locators, to other websites all around the net. And that information also has to be pulled in order to construct the web page. And so, in the absence of this open, free ability to connect everywhere, the web wouldn't work very well, or it wouldn't work uniformly no matter where you go. So, this openness has really served the internet well and continues to do so. And steps uh, to try to control what can connect to what really interfere with the utility of the internet and the World Wide Web. And so you'll find me and others pushing back against attempts to build sort of walled gardens around geopolitical boundaries. Now, that hasn't stopped some folks, like in China, to build the Chinese firewall and all that, the things that you've heard of before. But it's still the case that the design does not impose that kind of limitation. So I'm going to take advantage of some slides that I prepared, if I can find them here. Here we go. And theoretically, you should be seeing the first slide that says the future of the internet and AI. Is that, can I assume that's correct?
That's correct.
Okay, now I cannot see anyone now at this point because I'm only seeing the slides I'm sharing. So if anyone needs to interrupt, you should give me a shout rather than waving your hand or clicking on the raise hand button because I won't see that. So let me take you back in time to 1969. The predecessor to the internet was called the ARPANET. That was the Advanced Research Projects Agency Network. ARPA was created in 1958 in the wake of the Sputnik launch in October of 1957. Eisenhower didn't want to be surprised again and said, let's create an agency that will help us avoid technological surprise. They were funding the Information Processing Techniques Office of ARPA was funding research in artificial intelligence in the 1960s. And it was probably funding a dozen universities, ones that you would be familiar with, like Carnegie Mellon and Stanford University and MIT and so on. And every year, these science departments were asking ARPA to buy them a new computer every year to do world-class research. And we said, we can't afford it, but we will build a network and we'll hook all the computers together and you can share your software and your hardware. And by the way, we will fund everybody. So don't hide your results. Share your results so we can accelerate the pace of research. So this network was a prototype of a four-node system in order to test the idea that computers could be hooked together using packet switching. And it worked extremely well. It was quite exciting to see. This is very early days of packet networking. I was a graduate student at UCLA at the time, working on the Sigma 7. The Sigma 7's in a museum somewhere, and I suppose I should be there too, but here I am. This is what a packet switch looked like in 1969. It was the size of a refrigerator, and it was built into a very heavy duty metal cabinet because it was understood that it was going into extremely hostile territory, namely a place occupied by graduate students who like to fiddle with things. So this was a strongly protected piece of equipment. We were also very interested in mobile communications because, after all, command and control requires mobile vehicles, ships at sea, and airplanes. So at Menlo Park at SRI International, we had this nondescript looking radio van driving around, and inside there were these four white boxes that were packet radios. They operated at between 100 and 400 kilobits a second, which at the time in the early 70s was considered to be fast. Um, they cost $50,000 each, and so that's a far cry from what you have in your pocket or your purse today. Here you see some work going on packetized voice. So you imagine command and control often is a voice communication activity. We knew that we would need voice, video, and data in order to build a command and control system. And so these are some of the people who were testing packetized voice in a mobile radio van. You can see that we used very high tech Mickey Mouse telephones here to test the theory. I don't have a slide for it, but we were also testing packetized video, although we didn't have very much data rate, so we couldn't do very many frames per second. But you could see even back then, we're talking almost 50 years ago, that we were very interested in achieving what we now think of as commonplace today. What we are doing at this moment with the video conferencing and audio and everything else is exactly what we were doing that long ago, except in hugely larger quantity and with higher resolution. One of the most important aspects of internet is the fact that it allows multiple networks to be interconnected to each other, even though the networks themselves are very different in their operation. So the packet radio net in the Bay Area had a very different addressing structure and signaling mechanism than the ARPANET itself, and that was different from the packet satellite network over the Atlantic, which linked the west coast of Europe to the east coast of the U.S. So this demo was done in November after I had come to ARPA to run the program from there. Prior to that, I'd been at Stanford University pioneering the early design and implementation. So in this particular case, we had the packet radio van going up and down the Bayshore Freeway, sending packets all the way to USC ISI. Down at the lower left there, you see a little box that says ISIC. So San Francisco to LA is 400 miles. But the traffic actually flowed through the ARPANET to Europe and then back across the packet satellite net to the US and then down to Los Angeles so all three networks were carrying the traffic. The packets actually went 100,000 miles because there was an internal satellite hop on the ARPANET. It was at synchronous, so that's 22,000 miles. That's 44,000 miles round trip, plus another synchronous hop from Europe back to the U.S. over Intelsat 4A, another 44,000 miles. So now the packets have gone 88,000 miles plus back and forth across the U.S. And the Atlantic. So we're talking about 100,000 miles, and amazingly, it worked. And I remember leaping around in my office saying, it works, as if it couldn't possibly have worked. And those of you who know anything about software know it's a miracle when software works. So I was very happy with this very fundamental demonstration of multi-network interaction using the TCP protocols. In the mid 1980s, the US government engaged once again in the evolution of the internet. In this case, the National Science Foundation invested in building a backbone network to connect about 3,000 universities up to their backbone NSFNet, which also could reach the 5 supercomputer centers that were being jointly built by the Department of Energy and NSF. Department of Energy built their own, again, TCP IP based backbone network to link their data centers and laboratories together. And NASA did the same thing with yet another backbone network. The NSFNet has gone now and been replaced by commercial services. ESNet and NSINet still persist as backbone networks run by the government, but they are interconnected to the global network that now exists. So this is, speaking of which, this is what the internet looks like. Now I'm cheating a little. This chart was drawn in 1999, so over 20 years ago, but it allows me to illustrate what's going on here. There are tens of thousands of networks that are interconnected to each other. There's no central control. It's fully distributed. Each network chooses what business model it's going to use. Could be for-profit, non-for-profit, government-run. They choose what hardware and software they want to use. They choose who they will interconnect with and on what terms and conditions. And the only reason this all works is that they've all adopted the same protocol suite, which we now call the TCP/IP protocol suite. There is one center of coordination, however. It's called the Internet Corporation for Assigned Names and Numbers. It's run as an independent organization, although for many years it was under contract to the National Telecommunications and Information Agency, but that contract ended in 2016. It's now an independent international entity. They do the unique assignment of domain names, or top level domain names, and IP address allocations. Those IP addresses are allocated in big blocks to what are called regional internet registries, of which there are 5, and they are generally speaking geographically focused. So those coordinations are done in order to make sure that domain names get assigned uniquely to parties and IP addresses similarly assigned uniquely. Otherwise, the system just runs. Now, it doesn't run all by itself, and I want to acknowledge that it takes literally hundreds of thousands, if not millions of people to pay attention to the operation of the internet and make sure that it's functioning properly. Things sometimes break, things sometimes go wrong, mistakes happen, and people have to respond to that. So the network gets a lot of human attention to do what it does every single day. So the takeaways on this part of my talk are that we created administrative entities in the internet only when we realized they were needed. So, as an example, when Bob Kahn and I were both at ARPA and I was running this program, he said, "What happens if you get hit by a bus?" And I said, "Well, I probably get killed." And he said, "Well, that's the whole point. I want to make sure that what's in your head is available to other people so that if you get hit by a bus, the project doesn't disappear." And so we set up something called the Internet Configuration Control Board. And we picked that. I picked that name to sound as boring as possible, so nobody would want to be on that board. And then I selected the people to be on it as the heads of the research activities for the various parts of the internet. That morphed eventually into something called the Internet Architecture Board, which spawned the Internet Engineering Task Force, where standards are now made, and the Internet Research Task Force, where more advanced ideas are explored. So these entities kept getting created, but only as the apparent need arose. Another example of this is the Internet Society, which was created in 1992 because the National Science Foundation said we're not going to pay for the Secretariat for the Internet Engineering Task Force anymore because this is now becoming so commercial it should be supported by the private sector. So we created the Internet Society as a nonprofit in order to fund and house the Secretariat for the IETF. The other thing which is important, and I've already alluded to, is the diversity of the entities that are part of this ecosystem. They are loosely coupled to each other, in some cases in a very orchestrated way, like the interconnection among the various networks. But the interests are all over the map. And so it's not as if there is a dictated coherence to all this. And the entities that exist may span a lot of different functions. So, as an example, my company, Google, builds a very significant undersea cable optical fiber network to link our data centers together and to link ourselves and those data centers to the public internet. We have 8,000 points of interconnection to the public internet, for example. And others similarly are large in scale and have all those kinds of interconnections. And then others might be little local wireless ISPs. And of course, every one of us who has a small local network at home, an Ethernet or a Wi-Fi system, are also examples of entities that are part of this very complex environment. There are relationships among the various parties, and they are often formal and in some cases very informal. So, as an example, a lot of the interconnections among networks that make up the internet are on a handshake deal, not even a document of a contract or anything. It says you carry your traffic, you carry my traffic, and I'll carry yours. And amazingly, that probably represents 80% of the deals that are done to do interconnection. Now, there's a big problem when you want to do anything about sort of managing this complex enterprise, because I mentioned earlier, the packets flow across international boundaries without any, they don't notice that they've crossed one of these boundaries. So there are multiple jurisdictions in which parts of the internet operate. And when some jurisdictions try to invoke control over the system, they often introduce extraterritoriality, which bothers the other entities that are part of the system. So there's some complexity here with regard to the governance of the internet, how it's used and how it's operated. I've already mentioned the loose coupling. This system was turned on officially, operationally, in January 1st of 1983. So it's been running for literally over 40 years now. The design was done and first paper published in 1974. So we're celebrating the 50th anniversary of the design and, roughly speaking, the 40th anniversary of operation. The other thing which is notable is that the Internet Corporation for Assigned Names and Numbers and the Internet Governance Forum are all manifestations of what we'll call multi-stakeholder policy making. Once the policies get made, they may be executed by a smaller organization, smaller group, but we believe that policy should be made in the context of multiple points of view, and that's what we call multi-stakeholder policy making. So let's try to look a little bit towards the future. And this is not just the internet, it's the technology, computer technology especially. And in case you haven't already noticed, they're everywhere. I mean, we've got things that you and I use as personal devices, workstations and mobiles and smartphones and so on. And then the communications networks, which grew out of telephony, but which have become fundamental to wireless access to the internet in 3G, 4G, 5G, and eventually 6G, or Wi Fi for that matter, um, are all present and evolving. Edge computing is a term that you may or may not have bumped into. We started out by having small networks with terminals on them connecting to mainframe supercomputers and time sharing machines. That's evolved into laptops and desktops and pads and so on, and large scale data centers. And now we're inserting more computing at the edges of the net between you and the network that takes you to the data centers. It's called edge computing, and that's to allow for lower latency computation in case you need rapid interaction. Game playing would be a good example of the rationale for having that kind of edge computing or any other real time kind of application. Another thing which is happening is that devices are becoming internet enabled. So things that you wouldn't normally think of as having internet presence, like a light bulb, for example, or security system, or any of a variety of other devices. In Google's case, we have these smart home appliances that will play music, that will respond to voiced queries. They will respond to voice commands like, please put this on the shopping list, or turn the lights on, or turn the lights off. One thing that we didn't get right is the scale of addressing space that the internet is capable of supporting. We started out with a 32-bit address space, which would accommodate, if it were fully utilized, uh, 4.3 billion terminations. Now, at the time that decision was made in 1973, 1974, that was more than there were people in the world at the time. Seemed like that was more than enough for the experiment that we were performing. But by 1992, it became very clear that the number of networks in the world was exploding and the number of devices that were internet enabled similarly. So we've introduced a new addressing structure, a new packet format called IP version 6, which has 128 bits of address space. That's essentially 3.4 times 10 to the 38th addresses, 340 trillion addresses, which has got to be enough to last until after I'm dead. Then it's somebody else's problem. Those numbers are so big that, as I will tell you later, we are looking at a credible expansion of the internet across the solar system. And I'll come back to that in a bit later. I think you perhaps have also noticed that this term computational X, whether it's physics, chemistry, biology, linguistics, or sociology, or what have you, computers are now becoming core to the research community in every possible way, partly because more and more data is available and requires substantial computation to be ingested. All of you by this time know about and probably may have used large language models, which are the most recent manifestation of artificial intelligence. And they are both astonishing and puzzling and surprising. I'll come back to a couple of examples in another slide. We are building neural networks, machine learning networks, which is what large language models come from. Some of the most dramatic advances were made by one of our companies, uh, DeepMind, which built AlphaGo some few years ago to play Go, which is more complicated than chess. The program won 4 out of 5 of the games that were played with a grandmaster and captured quite a bit of attention. Then we wrote a new version called Alpha Zero, which learned how to play Go only knowing what the rules were and nothing else. And the programs played each other. The same, replicas of the program played each other and got better and better over time. The Alpha Fold is a machine learning system that figured out how proteins fold up after they've been correctly generated from messenger RNA, which comes from the DNA of biological systems. And what's interesting, of course, is that once you know how a protein folds up, you have some idea of how it will interact with receptors that matched the structure of the folded protein. So we now have a catalog of 200 million proteins that could be generated by human DNA. That catalog may help us find ways of either intervening to prevent disease from propagating or possibly enhancing some aspect of biological function. Cloud computing is essentially the modern day version of time sharing, which was invented way back in 1960, 60 years ago, except it's hundreds of thousands, if not millions, of processors available to the users. And it's gotten more and more interesting. There's clouds are interacting with each other, and the computers that are being used in the clouds are much more heterogeneous than they used to be. We have conventional central processing units, but we have graphical processing units. We have tensor processing units for doing specialized machine learning. And someday, perhaps, we will have quantum computing units as well. And we're working very hard at Google on that. And of course, in addition to all the other proliferation, data is everywhere. And without walking through this slide, which I don't think is necessary, I think you can appreciate that this massive amounts of information that's being generated and accumulated has the potential to make enormous advances in medical care, for example, by analyzing imagery or correlating treatments against disease or correlating a drug effect against a particular disease. And so much more. All of the things that the lower list there tell you that what's evolving out of all of this massive technology, the notion of data science, where data becomes an analysis of data becomes a fundamental driver to let us model complex processes. It allows us to do machine language development. We use the data to train. That should have said it's not just machine language, but also machine learning. That the large data components allow us to do that. We use the machine learning tools to do language translation and speech recognition and even speech generation. And of course, all of you are now by this time familiar with the generative artificial intelligence capabilities, which may someday lead to artificial general intelligence, but not yet. And in addition to all of that, communications has also evolved over time. Now we have low Earth orbiting satellites like Starlink and others that are on the way, Cooper and OneWeb, to maximize people's ability to get access to the internet from literally anywhere on the globe. So I thought I would switch gears a little bit and go to artificial intelligence for a moment and remind you that this research has been going on since the 1960s. I mentioned that earlier, that ARPA was led to create the ARPANET in order to support artificial intelligence research among collaborating universities and research institutions. We started out with this sort of heuristic systems that worked sometimes. If they worked, it was engineering. If they didn't work all the time, it was artificial intelligence. Then we had expert systems, which were an attempt to capture detailed, deep knowledge from experts and then encode this in if then else rules, if this, then that. And more recently, neural networks and machine learning have become fundamental to our use of computing technology. I'm replicating the previous slide here, so I don't need to bother telling you about more of it, except to say that the large language models especially have become objects of fascination. They're capable not only of generating text, but now also generating imagery and sound, which has led to a certain amount of consternation. So we'll talk a bit about that. We use these things for entertainment. You interact with a chatbot and you ask it to tell you a story, or you ask it a question and it produces a response. You might ask it to summarize a larger piece of text, and it's remarkable how well the system can actually do that. We use these same kinds of tools for image analysis and diagnosis of medical conditions, but we also have found that these things can hallucinate. That is to say, they make things up. They take factual material and they conflate things together to produce counterfactual output. And I tested this theory by asking one of the machine learning systems to write an obituary for me, and it produced a perfectly reasonable format. It gave said it started, we're sorry to report Dr. Cerf passed away, and it gave a date which was a little too soon for my taste. Then it went on to describe my career and family members, and it made up stuff that I didn't do in the career section, and it also made up family members that, as far as I know, I don't have. And I remember thinking, how the hell could that happen? And I realized that the systems, when they're being trained with text coming off the web or any other source, um, don't have context. So a paragraph with my bio and a paragraph with someone else's bio are not noticeably distinct to the training system. And so it could be plucking information from different bios and conflating them together and writing, for example, my obituary. So we still have work to do to somehow inhibit that kind of confusion from happening. The consequence of this is a lot of people are trying to constrain, control, or regulate the use of large language models and the use of artificial intelligence. For my money, we don't know enough yet about how these things work to actually regulate the technology, but we might say there are some applications that are high risk, and anyone offering those high risk applications should show how they have protected the safety of the users who are using those high risk applications. And if they can't show that they have protected those users' safety, for example, then perhaps they shouldn't be offering those kinds of services. And there are a variety of other applications that are becoming quite effective. Real-time language translation has become feasible as a result. Speech to text and text to speech is very commonly used, as well as now image and sound synthesis. That's gotten us into quite a bit of trouble because the systems can generate what, in effect, are fake images of recognizable parties doing and saying things they didn't actually do. And of course, you can imagine the concerns over that and the pressure for some kind of regulation to keep those fabricated kinds of videos and audios and imagery from causing confusion and problems. So I realize I have only 20 minutes left, and if you'll allow me another couple of minutes, I'd like to just quickly tell you about this dramatic expansion of the internet across the solar system. It started in 1998, just after the Pathfinder mission landed on Mars in 1997. A group at the Jet Propulsion Lab and I got together after the Pathfinder arrival to talk about what we should be doing back in 1998 to be ready for what we thought would be needed 25 years later, which is essentially today. And the decision we came to was that we should be designing an interplanetary backbone network to support manned and robotic space exploration. And we were partly motivated by the fact that we knew, even back in 1997, that there were future missions planned for landing on Mars that would require increased communication requirements to both for control of the devices, but also to recover the data that they had collected. So Spirit and Opportunity landed in January of 2004, Curiosity in 2012, and of course there have been other subsequent ones since that time. Here's a list of many of them, including the most recent Perseverance with its Ingenuity helicopter. So the interesting thing is, let me go back here for a moment. The interesting thing is that we started out thinking that we could use the TCP/IP terrestrial internet protocols to run on Mars, and we could. That would actually work okay. However, we started doing the math and we realized that the distances between the planets is literally astronomical, and that the speed of light is finite, and that the latencies between the endpoints in this network could be highly variable, some seconds, minutes to seconds, or sometimes hours to days or more. Just as an example, the sun takes 8 minutes. The light from the sun takes 8 minutes to get to Earth from sun, because the distance is 92 million miles. When you do the math, it takes that long. And to go from Earth to Mars, it's anywhere from 3.5 minutes one way to 20 minutes one way. And of course, to get to the outer planets, it's even worse. So the TCP/IP protocols of the terrestrial internet don't work very well in an interplanetary setting. So we developed a whole new suite of protocols we call the Bundle Protocol Suite. It is in operation on the space station now and has been for about 15 years. It is in operation in prototype form on Mars since 2004 and subsequently supporting the missions that landed after that. We are on board a recent mission called PACE that was launched just a few weeks ago as an Earth observer. So we are in the process of consolidating, testing, and validating this new bundle protocol suite for interplanetary networking. And we'll be part of the Artemis return to the moon missions. We're cooperating with ESA, JAXA, NASA, and CARI, the four of the major space agencies, to deploy and implement a backbone network. So by the 2030s, which are not very long from now, we expect to see a substantial investment in interplanetary networking. So I'll stop there, and we can go into our Q&A if you like. But thank you very much for letting me talk your ear off for almost 40 minutes here.
Thank you, Vint. Really appreciate the insights and history and futures thoughts. So I'm going to dive us into Q&A. And as a reminder, we do have a link for posting questions, and we'll get to as many as we can. So please do post questions through the link that is in the chat. Our first question comes from Miguel from the National Society of Hispanic Physicists. And he was asking if you would expand further on sort of the evolution and societal impact of the internet over the next 10 years, especially with the rise of AI, and how do you see that changing?
Well, it's clear that the generalized AI has offered us extremely powerful tools for dealing with text, imagery, video, and audio. It has allowed us to do analysis of vast quantities of data, looking for correlations, for example. And as my friends at UCLA remind me, who are working in this space, if you don't have a causal model to go along with analyzing the correlations that you detect with these machine learning tools, then you won't know what to do with the data, because correlation is not the same as causality. So we are, I think, racing ahead trying to find applications of machine learning, and some of which may turn out to be misleading. And we have to be very conscious of that. The generative AI stuff, particularly, and the example I gave you of the obituary shows you that we still have work to do to figure out how those generative AI systems can be coerced into producing things that are both coherent and accurate. Now, if it's just, like I said before, if it's just entertainment, the whole idea of ingenuity is wonderful. Creativity is good. What you don't want is made up stuff when you're doing banking analysis, financial advice, medical treatment, medical diagnosis, or other kinds of high risk applications. So we still have a lot of work to do to understand how these models can go off the rails, and how to design them so that they inhibit that possibility. I anticipate, though, that there will be some astonishingly powerful applications coming out of the large language models and machine learning models, including the ability to use neural signals or to generate neural signals that the brain will correctly interpret. So if you know about cochlear implants, you know we've come a long way to correctly generate a signal that the brain will interpret as sound. And you can imagine that happening with optical kinds of information, and also maybe with neuromotor information to try to help someone recover from a spinal injury. So we have huge potential here, but we also have some high risk. The ability to produce information which looks real but isn't, or looks like it's accurate but isn't. It may be deliberately misleading. it's forcing us into answer questions of jurisdiction and policy with regard to abuse of the technology. And the same problem is not just generative AI. Social media have also become a potentially toxic area, again, demanding some kind of regulation. And you see attempts by various countries, including the European Union, to try to get control over this. I think we're a long ways from understanding exactly how to accomplish that objective in a way that is that will work across the globe, because it's going to require international cooperation. You think about abusive behavior and accountability. How do you detect abusive behavior? How do you figure out who's responsible? How do you hold them accountable? And may need to have international agreements to do that. So there's a cybercrime treaty on the way that is supposed to help countries help each other, hold parties accountable when the victim is in one country or one jurisdiction and the perpetrator is in another. We have a lot of work to do, but I think we also have really important opportunities to put these technologies to work.
Thank you, Vint. Our next question comes from Alejandra from Princeton. What lessons can we learn from the development of the internet that can be applied to current issues and advancements in the world?
Well, one thing that's very clear is that collaboration was a core successful element of Internet's design and implementation. Second, we tried to keep it as open as possible. So if you didn't like the protocols that were available, you could make your own. You could extend a given layer of protocol by adding something, or you could add a whole new layer, which is what Tim Berners-Lee did. He looked at the TCP/IP protocols, which are the basic end-to-end communication mechanisms of the internet, and said, I'm going to create a layer called hypertext transport protocol. It sits on top of TCP/IP. Everything on the internet now has the potential to be part of the World Wide Web. We invented voice over IP, for example, in order to allow packet switched communication of voice instead of using the traditional circuit switching. So we can see how the openness of the system allowed so many parties to contribute new ideas without interfering with other people. And I hope we can retain that flavor as the internet continues to evolve.
So I'm going to build on that with a question from Nick, who is a Hertz fellow. How do you envision the role of emerging protocols like Nostra or even Bitcoin and Lightning, which are more open, versus emerging platforms which are more closed? So thinking about the protocols on the internet.
Yeah, I don't think of Bitcoin. Well, I suppose there is a protocol associated with that, so that's fair. I'm not a big Bitcoin fan, but that's because the idea that you should chew up a huge amount of electricity in order to get the answer to a question to earn another Bitcoin is sort of disturbing. However, the blockchain idea itself is useful, and we use it at Google, for example, for some of our applications like certificate transparency. So scaled appropriately, these kinds of systems can be quite useful. I think people have gone kind of overboard on cryptocurrency, to be honest. When people ask me about it, I tell them to run the other way. But that's, everybody gets to choose whatever they want to do. I think that the platform idea and the app idea that has arisen out of the mobile phones is a funny kind of walled garden, because the apps typically don't interact with each other. You have to be running the same app on various platforms in order to make them work, which in a way is the antithesis of the ability of multiple parties to implement something. So email is an example of an application that multiple parties implement and it interworks. But instant messaging has never interworked, and the reason is that the parties haven't agreed on the standardization of a procedure that allow different instant messaging systems to interwork. So it's disappointing in a way to see the emergence of these kinds of isolated applications. But I have to tell you, from the standpoint of getting something into the market quickly, if you build an app, you can propagate it everywhere that you can get into the Play Store. Whereas trying to get everybody, convincing everybody to implement your thing, which is what we had to do for TCP/IP, is much harder. So we can explore application space much more quickly with that architecture. And sometimes, of course, a popular application might drive us towards making interoperability a requirement or at least a feature. And I'd like to see more and more of that. But it does require a considerable degree of collaboration among the parties in order to make these things interoperable.
Thank you. I'm going to switch gears a little bit. Neil, another Hertz fellow, asks, how is the Internet of Things doing these days? Is its growth meeting expectations? What are roadblocks, and what should be done to mitigate or remove them? So, general assessment of the health of Internet of Things.
Yeah. First of all, there's still quite a lot of devices that are becoming internet enabled. And in some ways, I get worried about that because once they're internet enabled, how secure are they? How protected are they from abusive behaviors? Like the case where the webcams were not adequately secured and they were turned into botnets, which attacked one of the Dyn Corporation, 500,000 webcams that were part of your botnet army. So I worry about that. The other thing that is of concern is that different companies will build different devices, IoT devices, but they may use different protocol stacks in order to do that. So the devices don't interwork. And so if you're a customer and you buy devices from multiple sources, you may end up with a kind of incoherent household full of stuff. They have to use different apps in order to control the different devices instead of a common one. So I think there's still room for standardization there. Um, I used to think that some people thought this was just going to take off like a rocket. Maybe it's not quite as the IoT devices may not be taking off quite as fast as that. But it really is quite striking how many devices are starting to show up as internet enabled, all the way up to and including things like light bulbs.
I have a new washer that is being installed later today that seems to be internet enabled. I'm not quite sure if that's a good thing or a bad thing.
Well, let me give you a little scenario where you can turn a box of soap into a service. So imagine you have an internet-enabled washing machine and you have a stain. You got mayonnaise on your blouse or your formal shirt. So you go online and you search for a remove tomato stain. And you get a couple of websites, and one of them says, here's this Tide soap, which will remove the tomato stain. Would you like some help? And you say yes, and it says, okay, if you will enable me to do so, I will configure your washing machine to, with the right cycle, you just pour in the Tide or whatever it is, and the stain will come out. And so you've turned a box of soap into a service by having the machine online. Now, the flip side of this is the thing I used to talk about thinking it was funny. The headline I was worried about is 100,000 refrigerators take over Bank of America. And I thought, haha, isn't that funny? Well, it isn't funny anymore because, in fact, that kind of thing is not unrealistic. And to make matters worse, the refrigerator may be working perfectly well. It's doing everything it's supposed to do. It just has a little extra thing that somebody managed to inject in it to generate, messages to spam the world or to generate denial of service attacks. So the security folks have a long ways to go to make this a safer environment. And I think while I'm at it, I need to point out that security and safety are not the same. So you can have a very secure environment and still have somebody ingest a piece of malware through a secure encrypted pipe going from one website into your browser. And so safety is an even more complex problem than security. And both, of course, need to be attended to make us all safe online.
So you touched on, actually, you started touching on our next question, which comes from Christian, a Hertz fellow, and also Gradient Technologies, which is regarding edge devices. And he specifically asks, with the growth of the internet being dominated by edge devices, what are your thoughts on how we can secure communications?
Well, first of all, a core technology, of course, is cryptography, and it can be used for a variety of purposes. For confidentiality, we can use it for authenticity, we can use it for authentication, we can use it for integrity checking. So crypto is turning out to be really important. And some of you will know that the cryptography that we use today is subject to potential hazard because quantum computers could break the current public key crypto systems that are based on the difficulty of parsing the products of large primes. So, or factoring the products of large primes. So there are new algorithms that are based on lattice mathematics that are not subject to being broken by known quantum computer algorithms. So that's being pursued by NIST today, and there are 4 algorithms that are currently under consideration. We've already started implementing them at Google in anticipation that eventually the current algorithms will be broken, and people may want to preserve the confidentiality of their information for 20 or 25 years from now. So they don't want to use a protocol that could be broken then by Shor's algorithm on a quantum machine. So we still have a lot of work to do to get all that propagated, but I'm at least feeling comfortable that we have some ways of responding to the challenge.
We're approaching the bottom of the hour. We have several more questions lined up, and Vint has graciously agreed to stay with us for a few more minutes so we can get to a few more questions. But we know that a few folks are going to need to drop off. Just another plug reminder to please register for the summer workshop if you're able, and would love to see you there in Montreal. And the recording will be available after the fact for those who missed the tail end of the presentation. But with that, we will continue with our next question. Jake from Climistry asks, regarding electron spin as a novel communication method, what do you think the implications of spintronics research are beyond space communication?
Well, actually, spintronics is more likely to be of use in computation than communication, I would say. Although, if we can understand the state of photons, then those could be used for communication. And there's a great deal of excitement right now about using photonics in several ways. The simplest and obvious one, of course, is laser communication, which is generally speaking incoherent. Coherent laser comms is also extremely attractive. Spintronics could potentially allow us to build optical computers as opposed to ones that use electronic, properties, electromagnetic properties. So I am eager to see further evolution of the spintronic computation and spintronic communications. None of that will overcome the speed of light delay problem, however. So there are some people who imagine that entangled photons will somehow erase the communications delay to 0. And based on what little I know of quantum computing and quantum theory, that's not the case. That as soon as you try to set the state of an entangled photon with the purpose of affecting the partner photon, you destroy the entanglement. So all you get in photon pairs, entangled photon pairs, is correlation, but you don't get communication, which is very disappointing.
Thank you. I've got a couple of questions about the origins of TCP/IP, and then a final question that I want to make sure we wrap with. First comes from Jim from Amazon. He points out that it was impressive that you anticipated voice and video. He's curious about your prophecy on the progress of the QUIC protocol, as it appears to be progressively challenging TCP, and How,
Well,
what
yeah,
is the, what do you see as a long-term lifetime of TCP?
well, first of
Yeah.
all, I mean, Quick is a protocol that came out of Google. I didn't have anything to do with it, but I think it's a really good piece of work. It solves some problems that TCP did not. One of them is carrying multiple flow controlled channels in one common interconnect. So that's good for not having a head of line queuing problem. The other thing that Quick does, which TCP doesn't do, is collapse the time for recovery from a broken encrypted connection, because the Quick protocol generates a common variable, a constructed common variable, and it can be used in order to tell the other party, hi, I've moved to a different IP address, but I'm the same person, and here's my credentials, so to speak. So that's a nice feature as well. Of course, if both parties change their IP addresses, nothing works because you can't find the other guy. But at least if one of them moves uh, and the other doesn't, which would be a very common situation, for example, in mobile computing or mobile communication, it does very well. So I don't see these as necessarily competing with each other. Quick for certain applications is better than TCP, and I have no problem with that. For the same reason that I didn't have any problem with having to abandon TCP to develop the bundle protocol for interplanetary communications, because TCP didn't handle the round trip time delays and the disruption of interplanetary communications satisfactorily. So I'm in favor of anything that works better.
And Chris from Voca asks whether you could elaborate a little bit more on, as you were developing TCP/IP, what were the other candidate designs that you were evaluating, and how did it compare?
Well, interestingly enough, we didn't go through multiple choices necessarily. I think we were asking ourselves what fundamentally has to happen, and the design of TCP, almost we were forced into a particular design choice in order to make it work. Encapsulation was a natural element of the design. End-to-end acknowledgments was as essential in order to achieve reliability. Duplicate detection and filtering of duplicates and reordering was essential because some of the networks didn't keep things in order. So, the requirements were kind of dictated to us by the conditions under which this and assumptions that were being made. However, there were other designs. One of them was called X25 and X75, which was standardized around 1976, about the same time that we were deep into the TCP/IP development. But that was a virtual circuit design that came out of the telecommunications community and was quite popular. It was used by the banking systems very regularly, and there may still be some X25 around for all I know. Things that work tend to persist. The other competitor, a very clear competitor, was called Open Systems Interconnection. The work on that started in 1978, whereas the work on the TCP, what became TCP/IP, started in 1973. And so, just as I'm freezing the TCP/IP design so we can implement it on a bunch of different operating systems, the International Standards Organization, largely with European focus, started to develop the open systems interconnection protocols, which were in many respects very, very similar to TCP/IP. And so they competed with each other from about 1978 till 1993, roughly coterminous with the arrival of the World Wide Web and the increasing penetration of TCP/IP into the commercial marketplace. And so eventually the ISO work was abandoned, and TCP/IP became the preferred protocol for interneting among networks.
I lied. I'm going to ask one more question before I wrap up. What is the best way? Comes from Mahala. What is the best way AI can be used to address climate change problems and find global solutions faster?
Well, two possibilities. One of them is that AI may allow us to see correlations that we wouldn't otherwise see. Now, remember that a correlation doesn't necessarily imply causality, so we still have work to do when we see a correlation. But if AI allowed us to recognize that certain activities are critically involved in the global warming process, and if we can stay focused on how to mitigate those processes, that might help a lot. I would say quantum computing may turn out to be even more important, though, because in that case, we can do optimizations in almost real time in theory. And if you've ever used a spreadsheet, as I did when I got my first Apple II Plus, I had VisiCalc application allowed me to explore solution spaces by writing a spreadsheet program, changing parameter variables, and seeing what the results were. I anticipate we'll be able to do that with quantum computing as well, where we might get real-time optimizations on very complex phenomena. That's very exciting to me. Now, that's not the question you asked. That's an observation about the excitement I feel for quantum computing and optimization. So AI itself, I think, is still kind of a question mark with regard to its ability to produce explainable output that is reliable. And so I'm still, sort of hoping that we can learn how to do that, how to constrain the AI tools so that they don't produce misleading output.
All right, we have one more question that just came in. Alfred from MIT asks, countries are beginning to want to regulate their own national policies. It relates to the growing power of AI and data science applications. Sorry for the background noise. The US Senate is at the same time considering banning TikTok, which may soon realize access to the website. So where will all of this go?
Well, your guess is as good as mine. I will say that there are countries that would like to impose a set of rules, and the problem that we run into is that as they try to impose the rules on the internet in their country, they end up possibly creating an extraterritorial effect, and that causes other countries to say, "Wait a minute, we don't like that." This whole notion of data sovereignty, for example, I think is not a very useful concept. It's very appealing because people remember the Westphalian treaties, which led to the notion of sovereignty, of national sovereignty within this geophysical border or geopolitical border. These parties are in charge and you're not. The problem that we have with the internet is that we deliberately designed it so those geopolitical boundaries are not visible. Now, you could say, but what about the country codes, like .fr and .us and .de? Yes, but they're at a higher layer of protocol. They are way above the IP system, which is non-country centric. It is purely topological. So we do have an extraterritorial problem, and that's why there's a big debate right now about a cybercrime treaty to try to come to common agreements about how we can cooperate with each other to hold parties accountable for their criminal behavior. So I see the need for a substantial amount of collaboration and cooperation from country to country in order to achieve a safer internet for everyone.
I'm going to close with one final question from David, who's studying computational biology. Do you think living organisms will ever have formal membership in the Internet of Things? And if so, in what capacity?
The closest I can see that happening, honestly, will be some bioelectronic kind of interaction. I mentioned earlier cochlear implants. My wife has two. And I've often thought it would be fun to reprogram her speech processor to put TCP/IP into it so she could utter a question as we do with the Google appliance, hey, Google, mumble, mumble, what's the answer? And it would go out to the internet. It would come back. And of course, it would appear in her head. because it would come back as an electronic signal, which is transduced by the speech processor into neural signals, so the brain thinks it's hearing what the answer is. I thought it'd be really cool, because imagine you're taking an exam and you are heard repeating the question to yourself. What's wrong with that? And of course, the fact that your cochlear implant is going out and fetching the answer from the internet, of course, is totally invisible, because it's a Wi-Fi related thing, or it's Bluetooth or something else. So I've often toyed with that thought. I do anticipate that we may find even more refined ways of interfacing electronic equipment to our neural systems. Some of you are familiar with Elon Musk's neural link, which has made much finer grained ability to interact with neurons than a classic implant. The electrodes, in the case of the cochlear implant, are touching a substantial number of neurons. Each electrode does. So it's a rather crude, coarse kind of signaling mechanism. Something that's more refined might give us better processing, including optical, for instance. So but I think that most of this will be either neural motor or neural signaling, as opposed to people imagining that the computers will understand what you're thinking. There are experiments that suggest that we can almost do that. We can detect a few number of mind states, so you could express some mind state voluntarily and cause the system to associate that with an action. But it's not the same as having the kind of dialogue that we're having right now. So I'm not anticipating mind reading as an application, at least not in my lifetime.